Welcome back to Old School Math. Today we're going to be taking a look at transformations in vertex form. We're going to take a look at how to take a parent function, which we learned about in our last video, and make it move around the graph, shift it, translate it up, down, left, right, and that all starts by learning the vertex form. By the end of this video, you'll be able to identify the vertex of parent functions and write parent functions in vertex form based on translations. A couple notes here in this video. The vertex is the turning point on a parabola. If we graph the function y equals x squared, we would see a little dip in the bottom, and that bottom point is our vertex. It's going to be the maximum value if it's upside down, or the minimum value if it's just y equals x squared, our standard equation there. Now each function has a parent function with one important point in it that we'll look at for the vertex. We're going to use the term vertex pretty loosely in this video, since not every graph has a true vertex. Our parabola will, but you'll see some functions you'll say, well, that's not really a vertex, and you'd be right, but we'll still use that specific point in terms of our translations. Let's get out our note-taking guides and fill out this table together. So we have our different function families, and we've got parent functions here, and we're going to write the vertexes in this last column. So for our absolute value, we have f of x equals the absolute value of x. We would have a vertex on that one at 0, 0. As well as the line f equals x. The quadratic function, f of x equals x squared, also has a vertex at 0, 0. The cubic function, f of x equals x cubed, also has a vertex at 0, 0. The square root is a different type of function because it actually has a starting and a stopping point on the x-axis, but it starts and stops, or it starts here at the point 0, 0. Do we see a trend? Probably so. Cube root, it looks pretty similar to the square root, but we saw in the last video it actually continues all the way along the x-axis. We're going to take a look at that vertex point of 0, 0 as well. And then for our exponential function, it's the one that breaks the mold. It actually has a vertex at 0, 1. That's the only difference. Everything else, we're going to look at that vertex point at 0, 0. The vertex is really a good reference point for translating the graph left, right, up, and down. The vertex is always written as h, k. So that would be our ordered pair h, k, where h is the x-coordinate of the vertex and k is our y-coordinate for our vertex. We've got another table here. Let's fill this one out together. You can see in the linear function, we went from f of x equals x to the vertex form x minus h plus k. This one seems a little bit redundant to have parentheses around this when we could just do negative x plus k here together, but let's not worry about that one too much. And let's take a look at the absolute value and notice that we put the x minus h together inside of the absolute values, which kind of act like parentheses here, kind of bundling it together, and then plus k is on the outside. We see some similarities with our linear function here. The x minus h is in parentheses plus k on the outside. Let's see how that works for the quadratic function. F of x equals x squared. So our vertex form would be f of x equals, and then in parentheses, we're going to have, instead of just x, we have to keep the h with it, x minus h, and all that gets squared, and then on the end, we put our plus k. For our cubic function, it's going to look a lot like our x squared function. We're going to have f of x equals, and we're going to have, instead of x cubed, we're going to have x minus h cubed. Plus k. And then for our square root, that one's going to be a little bit different. Instead of putting stuff in parentheses, we're just going to bundle it together under the square root sign. So we're going to have x, or f of x equals the square root of x minus h, and then plus k is on the outside of the square root. So the x minus h live underneath, that's bundling together in kind of parentheses, and if you actually put this in your calculator, they would actually go in parentheses. The cube root will look a lot like our square root. We'll have f of x equals the cube root of x minus h, and then on the outside, again, plus k. And then our exponential, again, it's going to be the funny one in the group. We're going to put the x minus h together in parentheses in the exponent. So that's going to be f of x equals 2, and this is our base for our exponential that can change, to the x minus h power. And then on the outside, not in parentheses, we get a plus k. So we do see a pattern here, right? We see in every single one of these, the h value, that's the x coordinate of our vertex, is subtracted from the x in parentheses or bundled together in a square root or an absolute value sign. And then plus k is always just hanging out on the end. The plus k is the y value of our vertex, and that is what's going to give our up and down shift. The h is going to give the left and right shift. So again, transformations are really nice to look at as a big packet of functions here because they work the same way regardless of what type of function you're using, whether it's quadratic, cubic, square root, cube root, exponential, or linear. You can tell there's a nice pattern for all of these functions. H is always inside the parentheses with x, and it's always subtracted from x. The k is always on the outside of the parentheses. Now, this was a quick overview of just looking at vertex form for these function families. Be sure to watch the following videos that I'm going to have on YouTube for you, and you'll see how to use the vertex form to do translations left and right. And we're also going to look at reflections over x-axis and y-axis, as well as stretches up and down. We'll be able to take a standard looking graph like this is our cubic function, and do several things with it. We'll be able to stretch it, we'll be able to flip it, and we'll be able to move it left, right, up, and down. So stay tuned for the following videos. And as always, thank you for watching Old School Math. If these are helpful to you, be sure to subscribe.